Today I will tell about imidazole. First of all, we can add nitrogen in two ways in pyrrole, like that. This is pyrrole. We can add nitrogen in two ways. So we can write like this. This is called pyrazole. Or we can add nitrogen in another position. That is called imidazole. Now this is in pyrrole. This is C2 position, C3 position, C4 and C5 position. So we can add nitrogen at C5 or C2 position and C3 or C4 position. Pyrrole, pyrazole, imidazole, their basicity and acidity is different. In case of imidazole, imidazole is most basic among them because when we are taking imidazole here, this is imidazole and we add proton, so this nitrogen is sp hybridized and it will take that proton and become in positive. Now resonance is possible and resonance is like this will go towards this side, then this is the resonance. In imidazole, actually this nitrogen is the electron rich one, and if we are considering here electrophile addition, so in that case which position will be more electrophilic? In that case electrophilic position will be that C5 carbon 1 2 3 no sorry the position which is more prone towards electrophilic addition is the C5 position, and this is not the C5 position. The C5 position is this 1 2 3 4 5, and this is like in H, this and these two words and this. Now it will capture the electrophile. So if we consider about nitration reaction, if we add HNO3 as a electrophile, HNO3 H2SO4, the mixed acid, then NO2 positive is the electrophile. If we add HNO3 H2SO4, so NO2 positive is the electrophile here, and then NO2 positive will be added at the C5 position. That is like that. Mechanism is like, here is imidazole, and now here is NO2 positive. It will form. Now this hydrogen will deprotonate, then form again in presence of proton. It has a tendency to go in resonance, right? Now this hydrogen will release and if we take basic condition, then electrophile will be added at nitrogen. It is like you will go to resonance after anion formation on nitrogen. Then electrophile will be attacked at that nitrogen, and then in substituted imidazole will form. In will be in E is the electrophile added, or M double bonded O and O negative. Again it will go to resonance, tautomerization, then it can form like this and this. So if electrophile would be added, it will be added at the C5 position of imidazole. If we add acid, then the basic center is this nitrogen and proton will be added at that nitrogen. Now we will go to the synthesis of imidazole. So at first draw the imidazole molecule. This is our imidazole molecule. This is imidazole molecule. Here nitrogen place of X. This will be nitrogen. Okay. Now break it. We can break it in various position. So by applying retro, we can identify the reactant, and if we cut that in that position and that position, then the reactant will be actually by applying retro we get synthon. Okay, and the synthon is like, here is negative charge, here should be a substituent, that is TS, tosyl group, which active the acidity of that position, and hydrogen get easily detached from that position and anion forms, and anion gets stabilized by that tosyl group. Now here is a CN group, cyanide group present, and another properties, and here also a negative charge, here is negative charge, so it will get a positive, it will also get positive, that is applying retro we get the synchron. And this is R here, double bond in third butyl. Okay, third butyl actually we add because if there is a substituent in nitrogen, this is the nitrogen, and if it has a substituent R prime or here third butyl group, and so that substituent will be added that nitrogen, that imine nitrogen. So to understand add that I add third butyl group. If I add third butyl group here, that is substituted imidazole which has third butyl group in nitrogen. This is imidazole and third butyl group is here, and this is a R group. Then R group will come at that position of reactant, and third butyl group will come attached with nitrogen. Okay, now the reagent and the reaction mechanism. Now the mechanism is like this is our reactant and this is also our reactant. This is a imine. Actually we can generate it from ketone, we can generate that imine from ketone. Now we will add a base, that is third butyl amine, and that base will deprotonate that position. Actually this is not deprotonation, actually this is acid base reaction. That base captured that hydrogen and generate negative charge at that position, and we get negative charge here, double bond in third butane. As nitrogen is electronegative element, so that carbon attached with nitrogen, that is the imine carbon, is electropositive, and so that anion will attack to that electropositive center, and this bond will rotate, and then negative charge will come on nitrogen. So it will form here is negative and here is the third butyl group. Now nitrogen takes hydrogen from the medium and give positive, negative, tosyl group, R group in hydrogen. Now nitrogen have lone pair, and through its lone pair it will attack that carbon. This bond will rotate. This is actually 5-endo trig, means a 5-membered ring forms, and this is a endo bond rotation inward, and trig, that is a trigonal. Trigonal means as this bond is 180, this bond has 180 degree angle, so we will call it 5-endo trig. And 5-endo trig, according to Baldwin's rule, it is energetically favorable, and we get a ring closing reaction, and ultimately this is a imidazole structure, or it is tosyl group, this positive, that positive get neutralized by this hydrogen removal, then Then, as tosyl group is a very good leaving group also, so it leaves and double bond comes. So we are using tosyl group here. It is very important by using tosyl group we can generate anion easily, which stabilizes the anion, and which tosyl group acts as a good leaving group also. So double bond generation is feasible also here. So we are using tosyl group in the reactant, and the ultimate product is our declared imidazole substituted at in position nitrogen and at 5 position also. Another reaction mechanism is using Wittig reaction. By using Wittig reaction we can form imidazole also. Here the reactant is, this is also imine, but hydrogen molecule, hydrogen functional group is attached with that, substituted by phosphorus ester. The mechanism is like your tosyl group is attached, and this proton is the acidic proton. If we add 2 equivalent of base, that is sodium hydride, then this proton will be captured by base and anion will form. We are using here 2 equivalent of base because 2 acidic position is present here. One is this place, as this anion gets stabilized by this phosphorus group, and another is this anion which gets stabilized by tosyl group. So 2 anion will form. Now it will react with aldehyde and it will attack the aldehyde through this anion. Now it will form this O negative will attack to phosphorus and the OET group will leave and a 4-member ring will form. In negative and tosyl. Now Wittig reaction will happen and a double bond will form in that position by breaking the 4-member ring, and we get like that R can be cis or it can be in trans position also. This is the hydrogen part. Now if this anion attack to that place and this double bond rotated, then this will be 5 endo dig, and according to Baldwin's rule 5 endo dig is not allowed. So it will follow the mechanism, that is electrocyclic ring closing. Electrocyclic ring closing. So it will attack that position, it will rotate, and this bond will rotate simultaneously and a negative charge will come to that nitrogen, and Then the ring closing by electrocyclic reaction, and your negative charge come. Nitrogen contain tosyl group. The C5 hydrogen contain a substituent R. Now tosyl group will leave, and your hydrogen is present, will form now double bond rotation and our required product. This hydrogen will capture a proton. This is imidazole. Now its application. Peptide ulcers mainly form because of overproduction of gastric acid in stomach, and that acid gas acids are controlled by histamine in our body, and histamine contains that imidazole group. That is very much important. The histamine structure is, this is the structure of histamine. It controls acid production in our stomach, and this is the imidazole part, and this is acid, and this nitrogen takes this acid, and by resonance it controls acid production. Then NH forms, NH positive. Now again resonance, like that way, like that resonating structure, it controls acid production. For this reason, antipeptic ulcer drug cimetidine is developed to use as antipeptic ulcer drug, and cimetidine structure is like cimetidine. It is like NH. It contains the imidazole group, and this is as substituted portion NH Me double bond N Cn. This was about imidazole in short, and if this video is helpful to you, please like and share, and don't forget to subscribe to my channel. Thank you.